Welcome back to ECE 442-542. We are about a week away from exam number 2. We will hold a review session. This is in a different location. They're just making sure we're paying attention. This is in the ILC room 150 at 7 o'clock. I think the third exam review session will be where we had the first review session, but the second one is in the ILC room 150. Before that is homework number 4 is due, and exam 2, as I said, will be a week from Wednesday. There is some material that's posted that we have not covered in class, and you will need that on exam 2 and homework number 4, and that concerns the zero order hold equivalent of state space representations. How do you go from continuous time state space to discrete time state space? There's 2 parts of that. The first part goes through the theory, deriving those relationships. The second part actually looks at an example and walks through an example illustrating that process of finding the zero order hold equivalence of a state space representation. The goals that we want to address today are, 1, to summarize what those previous 2 lectures contain in another square. We'll have another square with different arrows going around. That's our summary square of the zero order hold equivalent technique. Then we will step into the other way of finding, or the other ways of finding discrete equivalents, and we'll categorize those into 2 different categories. One set are discrete equivalents, and we will actually develop 3 different ways of doing discrete equivalents using numerical integration techniques, and then we'll look at pole zero mapping. How do we find discrete equivalents using pole zero mapping? And the pole zero mapping, roughly, is we know our mapping between S and Z. Z is equal to e to the st. We basically factor our transfer function, if that's how it is given to us, into pole factors and zero factors, and we map those S-domain poles and zeros using that relationship, Z is equal to e to the st. But there's a few other subtle features of that pole zero mapping dealing with zeros at infinity, and we'll talk about that when we get there, which may not be today. Let me see if we can make this a little bit easier to see in total. Here is our summary square of zero order hold equivalents. This is a little bit busy. I'm not going to probably give you enough time to write this down, but I make the notes available so you can copy it and study it. You probably do want to write it down yourself. Maybe not now, but just to get a feel for what you're doing or what's going on. You have the left-hand side, which is the continuous time description and the time domain and the frequency domain, and that's from earlier courses, how to do that. And then we can jump over to the discrete time representations, either a state space representation, which is the material that we haven't presented in the formal lecture, but you'll have to look at and study on your own via D2L and YouTube. And then we can also go from the state space into the frequency domain using the Z-transform approach, similarly to how we Laplace transformed the state space and continuous time down into a G of S. Or if we start with a G of S in the frequency domain, we can do the lower equation in the lower right-hand block, which is the G of S over S technique of going from continuous time to discrete time using the zero order hold equivalent techniques that we've used before, or that we were talking about earlier. So this gives you a way of connecting or relating these different ideas, starting with one or the other of these representations, either in the time domain or the frequency domain, this gives you a block diagram type way of thinking of what you're doing, where the zero order hold up above, when you sample your continuous time system, you will end up with this system matrix in discrete time, which we're now using Greek symbols of phi. That becomes this matrix exponential e to the capital A capital T, which you can find numerically. If you're doing it by hand, you might want to do it using the lower equation, using inverse Laplace transforms on Si minus A quantity inverse. You inverse Laplace transform every element in that 10 by 10 matrix if A is 10 by 10 on the exam. Just making sure you're paying attention. But then you would have 100 inverse Laplace transforms. If it's an A matrix that's 10 by 10, you have 100 potential entries in that, and it's dependent on this variable S. But those are just your standard inverse Laplace transform techniques. You'll now have those in the time domain. You can put those into a sampled or into the e to the capital AT form by now replacing little t with capital T. And you will then pick a capital T appropriately. And what's appropriately in this class so far? If you're listening along online, you won't see me animating this rule of thumb that I was trying to indicate. I was sticking my thumb in the air. What's our rule of thumb for picking capital T? 30 times the closed loop bandwidth. If you're not going to close the loop, then you find your fastest mode and you sample 30 times that value in terms of determining capital T. If you are closing the loop, then you need to know how fast am I going to move this system or make it move in the closed loop, and base your capital T selection, your sample period selection, on that closed loop bandwidth that maybe somebody even tells you. They may say, I need you to speed this up, or I need the settling time to be such and such, and then you'll have to infer from that what is needed to find the closed loop bandwidth. Then the input matrix, this gamma in the upper right hand block, is found by an integral. B is a constant input matrix, so you can factor that in or out of the integral. Sometimes it reduces the number of terms in your number of integrals. If your matrix exponential e to the A mu was 10 by 10 and you had one input, you might actually want to collapse those 100 elements down and not integrate 100 elements, but you now have this 10 by 10 matrix of e to the A mu. Mu now is replacing t, wherever that was. Scale it by b, which is a 10 by 1, or multiply it by b, and now you have just 10 entries to integrate instead of 100. You've now reduced this 10 by 10 e to the AT. If you had that b factored out to the right of that integral, if you now move it inside the integral, now you have 10 element entries that you can integrate instead of 100. Sometimes it's to your advantage to slide that b in or out depending on your situation, is what I'm trying to suggest. That's in computing gamma, and you may want to look at that on your own. Now let's recall what we're doing. We've had discussed two scenarios, and we really worked with the second scenario, which was the zero order hold. Now we're trying to examine the first scenario, which is converting this analog system, let's say C of S, into a discrete time system, where now if you look at the block diagram, there is no zero order hold preceding that capital C of S, meaning we just want a direct replacement of C of S with C of Z. Meaning, if you have a analog filter represented by capital C of S, or you have an analog controller given by C of S, just think of a low-pass filter. We've already done that. You will just get a string of numbers in the discrete time setting coming in. You just want to generate a string of numbers coming out. You don't need to worry about holding those numbers coming in to the input, and that's why in this particular scenario number 1, we're not preceding our system, in this case capital C of S, with a zero order hold, and packaging those two together before we find the discrete equivalent. We're just trying to go immediately or more immediately from this transfer function capital C of S into its discrete equivalent capital C of Z, which is in contrast to what I've indicated in the lower with capital G of Z that we might use to replace the zero order hold, the plant, analog plant, and the D to A, no, I'm sorry, the A to D converter at the output side. That was what we've been doing so far, is our zero order hold equivalent shown in blue down below. What we want to do today is examine scenario number 1, which is where our analog system is not preceded by this zero order hold before we make this equivalent connection between the continuous time system and the discrete time system. We want to create an H of S or we want to convert an H of S or a C of S into a H of Z or a C of Z. That's what we want to talk about today, which is what we were calling scenario number 1. We want to now have this ability to not have to incorporate a zero order hold when we generate a discrete equivalent. It may not be necessary. And that's why I'm saying in these curly braces, capital H of S does not have to be a plant. It could be a filter. It could be a controller. And then we don't need to really worry about preceding our analog system or the continuous time system with a hold device before moving it into a discrete time representation, which in this illustration is capital H of Z. Here's what we have in front of us. We have 3 different categories of discrete equivalents. We started with the third one. That's what we've been doing up until this point, which was the hold equivalent, and in particular, our hold equivalent was a zero order. It was just holding it flat between each sample period. We've already covered discrete equivalent technique number 3. What's remaining is to examine technique number 1 and technique number 2. Today we will probably, I hope, cover forward, backward, and trapezoidal or bilinear numerical integration techniques. And it will essentially boil down to, if you have transfer functions containing S's, you're going to replace those S's with some collection of Z's or T's, something involving T's and coefficients and Z's. Everywhere you see an S, you're just going to plop in a combination of Z's, T's, and coefficients. And we want to today derive that lump of parameters, sampling period Z's and coefficients, that we will now place everywhere we have an S. So if we had an S squared, we would put that lump of parameters in where S was and square it, and then end up with some transfer function in terms of Z. We've now eliminated the f's. That's what we want to do in technique number 1. Let's then look at what that is. That's technique number 1, numerical integration. Let's sketch a picture of what we're trying to do. Let's say that curve is actually some waveform, x of t, and numerical integration is just what it says it is. We're trying to integrate the area, or find the area under that curve, x of t, by numerical integration. Let's now identify a couple of points on here. Let's say this time is t, and this width is 1 sample period in thickness. Consequently, this point to the left of little t is little t minus capital T. And we will actually use little t, or we will set little t equal to, or we will sample the time axis. We will subdivide it in terms of integer multiples of the sample period capital T, meaning little t is now some n sample periods into this waveform x. That's our picture. What we want to do then is, as we said, we want to generate the area underneath that curve. We want to now find y of t, which is the integral from 0 to t of x, let's say, of tau d tau. That's our normal way of thinking about the area underneath that curve, where the curve's top is x, is the function x of t. Let's establish some terminology. Let's now let y of t be the area under the curve x of t up to time little t, and we will define another variable, y 1 sample period before little t, which is y of little t minus capital T, and that is consistent with the first definition of y of t, but now we have the area under x of t up to time little t minus capital T, which means that we could say, oh, here is our y of t, and the green is y of little t minus capital T, and if we want all of the area up to little t, then we would consider both shaded intervals, or both shaded areas, to create that. That's the picture that we want. And we can actually write that in terms of these two different definitions. We can now say y of t is equal to y of t minus capital T plus the integral from little t minus capital T up to t, x of tau d tau. That should be consistent with our picture. We have maybe the green shaded area, that's little y of t minus capital T. Maybe I should have done it this way, huh? color code it. Then I have this other piece, or this other area, which is the area under that little sliver, defined by the integral from little t minus capital T to t, little t, of x of tau d tau. Like I said, if we let our time axis be divided up into integer multiples of the sample period, then we can rewrite this expression as y of t is equal to y of n minus 1 cap t, if I factor out the capital T, plus the integral from nt minus t to nt x of tau d tau. I really haven't done too much. This should be believable as far as what I've done so far. Now, I indicated going into this that we were going to look at 3 different numerical integration approaches, and they all hinge on what we really do to approximate this term that I've indicated by this red underline. The different numerical integration approaches or techniques, different numerical integration techniques are actually based on how this integral from nt minus t up to nt x of tau d tau, how that integral is approximated. And hopefully these different approximation techniques are somewhat connected with the terms that we use to describe these rules or techniques. The first one that we will look at, we will refer to as the forward rule. Again, we're looking at a numerical integration techniques. We're calling it the forward rule, and with this forward rule, what we are doing is we will approximate that integral above, now actually with a rectangular area. With the rectangular area, and that's why it's an approximation. And it's a forward rule, meaning we are going to be looking forward to make that rectangular approximation of that little sliver. We will look forward from x at time n minus 1 capital T, which if we go back to this picture, this point right there is x of n minus 1 capital T, and this point right there is x at nt. In the forward rule, what we are doing is we are saying just assume that we are looking forward from x at time n minus 1 capital T, and now you can see that we've approximated this sliver with a rectangle. And now the area of that sliver is approximated by a rectangle that's not very difficult to define. It's just the height of that rectangle, which is given to us by x at time n minus 1 capital T, and the width, which is the sample period capital T. If we use that approach, then what we're saying is we are going to take this integral from nt minus t to little nt of x of tau d tau, and that's now going to be approximated by the width of that rectangle, which is capital T, and its height, which is x of n minus 1 capital T. That means in this expression right here that I have in blue, green, and black and red, I guess red is not in the expression, it's just highlighting the part that we are approximating. We can now rewrite that equation with using our forward rule approximation, and we now can say that we have y at little n capital T is approximately y of little n capital T minus capital T plus this approximation of the integral, which now is capital T times x of nt minus t. Where this, I just multiplied it out, but it was just the little, or quantity, little n minus 1 times the sample period capital T. That's now our approach to finding the area underneath that curve, where that curve was governed by x of little t. And we've now segmented that time axis up into pieces determined by the sample period capital T. That's a time domain, a discrete time domain representation. Let's transform that equation. Let's obtain a frequency domain representation or description of that equation. If we now z transform, since we have a discrete or a difference equation, we can now z transform. What's the z transform of y of little n capital T? We don't need to know what little y of nt actually is. We're doing this basically symbolically, or we're doing it with just variables. So we can say, let's just define the z transform of little y of nt to be capital Y of z. Let's just make that definition. That makes this development fairly straightforward. We can now say, okay, the left side I'm simply going to call capital Y of z. And now I'm going to know that we are approximating, but I'm going to forget the approximation sign and just say that's equal to. Now, if little y of little n capital T is capital Y of z, when we go from time domain to frequency domain, what's the first term on the right going to be equal to? That's just a delay of one sample period, which in the frequency domain is z to the minus 1 of capital Y of z. Does that seem reasonable? Little y of little n capital T delayed by one sample is just in the frequency domain capital Y of z scaled by this operator z to the minus 1, which is a one sample period delay. Now if we take the next term on the right into the frequency domain, capital T is just fixed. That's a fixed number. And how do we rewrite little x using the same thought process that we found all the y's. If little x of nt gave us capital X of z, then this one, which is delayed one sample, must give us z to the minus 1 capital X of z. And let's now combine terms. If we pull the y of z terms to the left, we can say we have 1 minus z to the minus 1 capital Y of z, and that's equal to t z to the minus 1 capital X of z. And we can find the transfer function that relates y of z to X of z by dividing both sides through by capital X of z, dividing both sides through by 1 minus z to the minus 1, or that term, and we have t z to the minus 1, 1 minus z to the minus 1. Maybe you don't like the way that looks with all those z to the minus 1s floating around, but you know how to change that. You can multiply it by 1. We can always scale things by 1, and the 1 that we will use is simply z over z. If we hit that right-hand side with z over z, we end up with t over z minus 1. That's now this relationship between, let's say, the input, x, and the output, y. But what is this doing in, let's say, the time domain? If we were to think about this in the time domain, what is this doing if we went back into the time domain, this right-hand side, this transfer function? What did we do to create this right-hand side? What was the starting point for that? Or let's go back and recall where we started this process. If we look at the continuous time expression, which is what we started with, we had y of t equaling, let's say, 0 up to t of x of tau d tau. That was y of t. That was the area under the curve from 0 up to time t. If we put that into the frequency domain, what do we have in terms of s's? Y of t becomes, if we Laplace transform this equation using the same thought process that we had before, we just generically say, oh, well, y of t is a generic signal, and we're Laplace transforming it. We can take that into the s domain simply by capitalizing that y. The left-hand side becomes y, capital Y of s. What's the right-hand side become? That's just an integral in the frequency domain, which is 1 over s, capital X of s, which says that y of s over x of s is 1 over s. And what we want to do now is say, oh, we want a strategy for relating s's and z's. And now we have it. Here's a right-hand side in s's, 1 over s. That's an integration. Well, we derived an integration in the discrete time case relating x and y, and it became the right-hand side, capital T over z minus 1. If we then compare those, which is what I just did, we can now say that the Laplace expression, 1 over s, you could relate that to the z-domain quantity, which is now capital T over z minus 1. Well, 1 over s, we can invert that if we wanted to think about what is s in terms of z. We can just say, well, let's invert that, and now s is related to the inverse of the right-hand side, or it's now the quantity z minus 1 over capital T. What this allows us to do then is to move from a c of s, a transfer function, let's say c of s or h of s, into a c of z or an h of z. By everywhere we had an s, we replace it with this expression on the right, z minus 1 over t. And that's a discrete equivalent using the forward rule of numerical integration or approximation. That's how we derive this connection between s and z. And that's how we will describe it. But here, what we're doing, if we wanted to make this discrete equivalent, we will replace all of these s's with z minus 1 over capital T in, let's say, h of s to obtain the discrete equivalent h of z. Let's look at an example. Suppose we have capital H of s equal to a over s plus a. Now you're on a job interview and somebody goes, here's a transfer function, capital H of s equal to a over s plus a, and they go, tell me about it. What is that? After you've swallowed deeply and taken a deep breath, what do you start? You just relax. You just take a deep breath. And what do you tell them, your interviewer? They give you a over s plus a, and now they want you to expand on what they've given you. What would you start telling them, or what's maybe one of the descriptions you might relate to them if they give you a over s plus a and say, what is this? What would you say? No, you don't start meditating. Well, you could, I guess. I told you to take a deep breath. What does that represent? You could take it into the time domain if you want. If you know what these interviewers are looking for? Basically, if you can sort of think on your feet. So now you say, well, this must be the transfer function between two variables, an input and an output. Let me see what this looks like in the time domain. Maybe that's your first thought process. What I was hoping you would do is you would say, that's a first order system, right? Has a denominator with one factor, one power of s. It's first order. And I hope that after today's class you go, I could actually kind of think about that in terms of a Bode plot. That's actually just a low-pass filter. Yes? What's the DC gain of that transfer function? You have a first-order system with a DC gain of a over a, 1. What happens as the frequency gets higher? As s gets bigger, you now are looking at the frequency response. You're replacing s with j omega. You now have a over j omega plus a. You let omega get big, and what's happening to h of j omega, the magnitude? The denominator's growing, the numerator's not changing, so the whole thing is starting to get smaller. You're filtering, you're attenuating higher and higher frequencies. As the frequency, as omega gets bigger, your H is getting smaller. That's a low-pass filter. You favor low frequencies because you just told me the DC gain was 1. At S equal to j omega with omega equal to A, you're now at that sweet spot. You're at the corner frequency. You now have the half power point. That's your break frequency in these straight line approximations. You could simply sketch a straight line magnitude response for your interviewer and say this is a low pass filter with a cutoff frequency of A. And then they'll move on to the next question. What we want to do now is make a discrete time low pass filter using numerical integration and the forward rule for doing that. But now you have identified this as a low-pass filter. And we've already sort of made some observations. With respect to this analog system, I mean, if you couldn't see what the interviewer was trying to get you to think about, you could just start telling him or her what this H of S has. It has some poles and zeros. Where's your pole? It's the value of S that causes that denominator to vanish or to be equal to 0, and that's when S is equal to minus A. Do you have any finite zeros? Any finite values of S that cause the total thing, H of S, to equal 0? Now you're looking in the numerator and you're saying, do I see any S's in that numerator that will cause the numerator to go to 0? That would cause the whole thing to vanish. There are no finite zeros. Contrast that in a little bit, we'll need to worry about infinite zeros. Are there any zeros at infinity? Meaning, are there big values of S that cause H to vanish, and how many of those are there? And that hinges on the order of your denominator. You have a first order denominator, so you have the denominator is 1 order bigger than the numerator. You have 1 0 at infinity. You can let S get big, that 1S get big, and you'll get H of S going to 0. You have 1 0 at infinity. Because you have, and this maybe you're familiar with from earlier classes maybe, the pole 0 excess. What's the pole 0 excess? How many more poles do you have than zeros? 1. That tells you you have 1 0 at infinity. And we know what the DC gain is for this analog system. That's what this expression equals when we let S or set S equal to 0. That's now A over A, or 1. Let's now replace capital H of S with capital H of Z. Let's create a discrete equivalent. We can now say, okay, let's do this forward rule that we've just developed. And that's just one particular strategy or technique for finding an H of Z given an H of S. And I will call this particular approximation, I'll subscript it with F for forward. H sub F, H sub forward of Z, is now going to be found from H of S when we allow S, everywhere we see it, to be replaced with the expression Z minus 1 over capital T. And I've picked a very difficult H of S. I only had one S in there, so this isn't that hard. I have an A. There was no S upstairs. There was one S in the denominator. And that's all there is to it. That's now my H sub F of Z. Although I might want to clean it up. Maybe I'm not used to seeing excuse me, transfer functions that look like that, but I can again clean it up by multiplying by 1, hitting both top and bottom, or numerator and denominator, by capital T, and I now have AT over Z minus 1 plus AT, or I have AT over Z minus 1 plus AT. And that's now a discrete time transfer function that's a low-pass filter, and you could create a difference equation. You could implement this in Excel, in some microprocessor, if you took this y over z relationship back into the time domain, using these coefficients, little a, capital T, etc., where z is an advance of 1. But let's look at what this is. So this is H sub F of Z. We looked at some continuous time properties of capital H of S. Where's the pole for this discrete time transfer function? Poles and zeros, the definitions haven't changed any. The pole is the value of z that causes the denominator to vanish. We set the denominator equal to 0 and solve for z, and we find that that's now 1 minus little a capital T. And where will that live? Where will that belong for a particular A and a particular capital T? Do you see where the pole is? Is it real? Is it complex? There's only one pole, so it can't be complex, can it? And it's between where? In the z-plane. It's near 1 if A and T are both small, but it's inside the unit circle, isn't it? And it's between 0 and 1. And where it is between there will depend on what A and capital T are. Do you have any finite zeros? Any z values that cause that H of Z to vanish? No, so there are no finite zeros. What about the DC gain? How do I find that? The DC gain of H sub F of Z. How do I find it? How did I find the DC gain of H of S? What's DC in the S domain? That's 0, isn't it? That's the origin. Where's that equivalent point in the z-plane? And you know your mapping. Your mapping is z is equal to e to the st. And you just said s is 0, e to the 0 is 1. So now dc, to find that, you're evaluating this at z equal to 1. We now replace z everywhere, and it only appears once. We put it equal to 1. We now have at over 1 minus 1 plus at over at. No matter what those two are equal to, we still have a DC gain of 1, which is good. That's consistent with our original analog transfer function. And you could use that first order system in the discrete setting to find a linear difference equation. Now you have a first order linear difference equation in the time domain. And that's corresponding to the forward rule of numerical integration. Let's look at another rule. And the rule was determined by how we approximated that little sliver in our integration. The next rule is the backward rule. And in this case, what we want to do is we want to approximate the integral again with a rectangular area, except this time we're looking not forward but backward. And if it's the same sliver, we need to look back from x at time n, little n, capital T. With rectangular area looking backward, from little x, capital T. Which means now if we have this integral of nt minus t up to nt of x of tau d tau, we are now approximating that with the width, which is our sample period, but now we're looking back from the most distant point, little n capital T, or the value of x at that point. And if you go back to our picture, wherever that was, now we are approximating that area based on that shape of x of t. Now we're underestimating that area in that interval. Before, with the backward, we were overestimating in that particular location of x. But do you see the different approximations? And if that sample period is small enough, those approximations are not going to be that inaccurate. This now allows us to write down y of nt is now approximately equal to y of nt minus capital T plus this approximation of the integral of that little rectangle, which is capital T x of little nt. Now if we do the same process that we did before, we can take this into the frequency domain by transforming it. We now have y of z is equal to z to the minus 1 capital Y of z plus t x of z. That now gives us this t over 1 minus z to the minus 1. We can clean that up by multiplying both top and bottom by z. And we have now tz over z minus 1. Again, this is consistent with integrating in the time domain. And we can again compare transforms in the frequency domain. We had in the S domain an integration operation was simply this 1 over S. Now that becomes what we have right here, which is tz over z minus 1. But we may not want to think upside down, so we invert everything and we say, oh, let's relate S now, or replace S everywhere with this backward rule. We would replace it with the quantity z minus 1 over tz. And this is now the strategy that we would use if somebody said use the backward rule of numerical integration. We replace S with the quantity z minus 1 upstairs divided by capital TZ in h of S in order to obtain h of z. And if we go back to our example, and apply our backward rule, we can now say that h sub b of z is h, capital H of S, with S everywhere replaced with z minus 1 over capital TZ, or this is now A over z minus 1 over TZ plus A. That may look a little bit messy, but we can clean it up again by multiplying everything by capital T little z, so that now our backward rule numerical integration approach for approximating this low-pass filter becomes ATZ over z minus 1 plus ATZ. Or that's ATZ times 1 plus ATZ minus 1. Again, we can start looking at properties of that numerical approximation, or numerical integration technique for approximating this low-pass filter. Where's the pole? We set that denominator equal to 0 and solve for z, and we now have 1 over 1 plus little a capital T. Where's that going to reside? Is it in or out of the unit circle? 1 plus AT for a positive A and a positive T, that's bigger than 1. You're dividing 1 by something bigger than 1. You're now inside the unit circle. Again, you're real and you're inside this interval between 0 and 1. What's the DC gain? We can let z equal to 1. The numerator becomes AT. The denominator becomes 1 plus AT minus 1, or AT over AT, which is 1. Good. The pole may be a little different location. Do we have any finite zeros? Are there any finite values of z that cause h sub b of z to vanish? And there is, isn't there? Now you can let z equal to 0. You're now at the origin in the z-plane. And that's now a finite 0. This guy has a little bit different pole 0 configuration, but it's an approximation of the low-pass filter. That 0 at the origin is very, very fast. If you think about the speed of your system being if it was a first order, if I had a pole at 0.9 versus a pole at 0.1, which of those poles would produce a faster system? Now, when I say fast, you're thinking, how quickly do they collapse? If you scale something by 0.9, or if you scale something by 0.1 every time, which one's shrinking quicker? The one that's closer to the origin. That's the fast one, isn't it? Here you're right on the origin. That's really, really fast. So this 0 is a really, really fast 0 that you could almost think of as being infinite. But we've all also thought about z equal minus 1 as being infinite in this frequency domain plane of z. So we have some different ideas or concepts, and we'll also talk about zeros at infinity. But let's move on to the next numerical integration approach, which is the trapezoid rule. Those rectangles were just a little too boring. Let's now create a trapezoidal approximation to that little sliver. We want to now approximate the integral by a trapezoid, which means the top of that sliver is going to be at having some slope. We are now approximating this integral from little nt minus capital T to little nt of x of tau d tau. That's now approximated by, we still have the same width, it's just now we're taking really the average of the rightmost endpoint and the leftmost endpoint of the height of that x of t curve or waveform. We now have x of nt plus x of nt minus t all divided by 2. And if you wanted to think a little bit more about this, this is really like you're averaging the forward and the backward rules. So you're sort of taking a compromise between those. This is like averaging F and B. Sounds like a band. You're averaging F and B, or it's not R and B, I guess, it's F and B. Oh well, it's getting late. Not that late, but now what do we have? We have now our difference equation is this y of nt is approximately y of nt minus t. We're now replacing that integral, we're approximating it with this capital T over 2 times x of nt plus x of nt minus t. What are we going to do? We're going to go into the frequency domain again. Let's look at this in the frequency domain, which says now the right-hand side, or I'm sorry, the left-hand side becomes capital Y of z. The right-hand side is z to the minus 1 capital Y of z. The second term on the right-hand side becomes capital T over 2, 1 plus z to the minus 1 capital X of z. And if we now solve for this relationship of y of z over capital X of z, we now have capital T over 2, 1 plus z to the minus 1 over 1 minus z to the minus 1, which we don't typically like to work with z to the minus 1s. We now have 2 over t, z plus 1 over z minus 1. But that's the integral comparison, if we compare transforms, one over s can be compared to that we just derived, which is capital T over 2, z plus 1 over z minus 1. But if we were wanting to make this substitution of s for an expression in z, we would say s we can relate to the reciprocal of what we just derived, which is 2 over capital T z minus 1 over z plus 1. Which, if we now want to use this trapezoidal rule for numerical integration, we now replace s, or all of the s's that are in this transfer function, capital H of s, with 2 over t times z minus 1 over z plus 1. We use that in capital H of s to obtain a capital H of z. And let's do that for our low-pass filter example. And you might see this referred to as a bilinear transformation in this or other classes. So I may use either the trapezoid rule or the bilinear transformation to mean this same numerical integration approximation approach. We have H of s is our first order low-pass filter, a pole at minus a DC gain of 1. We now want to find H sub t for trapezoidal of z. That's now H of s, with s everywhere replaced with capital 2 over capital T z minus 1 over z plus 1. Now we have a over s, which is replaced with 2 over capital T z minus 1 over z plus 1 times 1 plus a. It's getting late. And we can clean that up if we want. We can multiply by capital T z plus 1, or put everything over that in the denominator, and that will then pop upstairs, and we now have AT z plus 1. This is H sub t of z of 2 z minus 1 plus AT z plus 1. Or, if we collect coefficients for z and constant terms, we now have 2 plus AT scaling z plus AT minus 2. And upstairs we still have this AT z plus 1. Where is our pole now? We can set the denominator to 0. We can now say 2 minus AT divided by 2 plus AT is where our pole is. Does that seem like it's reasonable? AT is a small positive number. We're subtracting that from 2, so we have something a little less than 2 upstairs. We have something a little bigger than 2 downstairs. That's less than 1. Good. And it's real. We didn't have any complex numbers floating around. Do we have any finite zeros? And where is it? It's where we kind of thought it might be. It's at infinity, in a sense. -1 is really, really fast in the z-plane. That's on the unit circle, and that's really as far as we can get when we think about our frequency variable in the z-plane. If we were walking up the imaginary axis in the s-plane, that's the omega, that's our frequency response. Now we're moving along the unit circle, and the furthest we can go is to -1. Can we compute our DC gain? Again, we set z equal to 1 in that expression. The numerator becomes 2 times AT. The denominator becomes same thing, right? And that's what we wanted. Now, these numerical integration approaches are approximations. Do we preserve the right properties or some of the properties that we started with in the S domain when we use these numerical integration approximation techniques? And one of the key properties that we might be interested in is the fact of, is stability always preserved with numerical integration? By that I mean if we use the forward rule for a discrete equivalent, if we start with a stable system, do we end up with a stable system when we get it into the z domain, h of z? Do we end up with all of our poles in the unit circle? We want to now check the mapping from the S-plane to the Z-plane for each of these rules. Our first rule was the forward rule. In that rule, we were replacing S with Z minus 1 over T, but now we want to know, what does Z look like for all these different values of S? We can solve for Z if we just set these two equations equal, or two sides equal to each other, and we now have 1 plus ST. Let's say this is the S-plane. Stability is every point over here. Now if we map using Z, if we now go Z equals 1 plus ST, where do those points in the S-plane end up in the Z-plane? Here's our Z-plane. And you could just start thinking about each of these points in the S-plane. and plotting those one for one into their corresponding point in the z-plane using this mapping. Z is equal to 1 plus s capital T. If we start at the origin, we map to 1, don't we, in the z-plane. If we started somewhere else, let's say some other place, what are we really doing? We're really just sort of shifting everything, or this particular line is a defining line, and we're actually shifting the plane. Whoops, I meant to be a different color, but now we're over here, and does that preserve stability? Now we really wanted to be inside that unit circle for every point that's in the left half plane, and this forward rule does not. The backward rule will, and so will the trapezoid. We're not going to have time to go into that, but the backward maps into a very small area within the unit circle. The trapezoid maps everything, the S-plane, the left half S-plane, right onto the entire unit circle. We'll pick up somewhere close to that on Wednesday.